Look up at the night sky on a clear evening. You see stars, planets, the faint band of our Milky Way. It feels vast, almost eternal. But what if I told you that this isn't the real background of the universe? That there's something far older, far more fundamental, a quiet hum of ancient energy that fills every single cubic inch of the space between those stars, and even the dark emptiness between galaxies. This isn't science fiction. This is the cosmic microwave background, the oldest light in existence. It's the lingering echo of the universe's birth, the afterglow of the Big Bang itself, and it's bathing you in its faint whisper right this very second. It's a cosmic fossil, and it holds secrets about everything, how it all began, what it's made of, and perhaps how it will ultimately end. For decades, we've pictured this afterglow as a nearly perfect, uniform blanket of energy, a smooth, featureless fog left over from the fiery dawn of time. It's the ultimate baby picture of the cosmos, but what if that picture has tiny, almost imperceptible flaws? What if, etched into this most fundamental canvas of reality, are strange blemishes, puzzling irregularities that whisper a story completely different from the one we thought we knew? These aren't just random specks of noise. They are profound anomalies, cosmic paradoxes that challenge the very foundations of modern cosmology. Some look like cold spots impossibly large. Others suggest a strange lopsidedness to the entire universe, and a few hints might even point to events that occurred before the Big Bang. This uniform fog, it turns out, is a parchment scrawled with cryptic messages from the dawn of time. So, the question we're going to explore together is a thrilling one. What if the oldest light in the universe is trying to tell us a secret? And what if we're only just beginning to learn how to listen? This video is a journey into those deepest mysteries. We're going to decode the enigmas written into the cosmic microwave background, to explore the 25 most compelling puzzles that have scientists both fascinated and, frankly, a little bit baffled. We'll travel from the instant of creation to the very edges of theoretical physics, investigating clues that could rewrite our understanding of reality. So get ready. We're about to pull back the curtain on the cosmos and read the story written in its first light. To truly grasp the first and perhaps most fundamental mystery, we need to perform a simple thought experiment. Picture the cosmic microwave background as a vast spherical shell surrounding us, a surface glowing with a nearly perfect temperature of about 2.7 degrees above absolute zero. Now pick two spots on this shell that are directly opposite each other in the sky, as far apart as it's possible to be in our observable universe. According to our best measurements, these 2 points, separated by a staggering distance of over 90 billion light-years, have exactly the same temperature. They are in perfect thermal equilibrium, and this is the problem, a colossal problem known as the horizon problem. Why is this so baffling? It comes down to a simple, unbreakable rule in physics. Information cannot travel faster than the speed of light. Heat is a form of information. For two things to reach the same temperature, they must have had time to exchange energy, to communicate and settle into a common state. But if we rewind the cosmic clock back to the moment the CMB was released, about 380,000 years after the Big Bang, we find something startling. Those two opposite points in the sky were so far apart that light itself from the moment of the Big Bang would not have had enough time to travel between them. They were born forever beyond each other's cosmic horizons, completely causally disconnected. It's as if you had 2 cups of coffee in separate, soundproof rooms that had never been connected, and yet you find they have both cooled to the exact same temperature, to the millionth of a degree. Under the standard Big Bang model, this perfect uniformity is not just unlikely, it's effectively impossible. This is where a truly radical idea enters the picture: cosmic inflation. Proposed in the early 1980s, inflation suggests that in the very first fraction of a second of the universe's existence, an almost inconceivably brief period, perhaps as short as 10 to the power of -36 seconds, the cosmos underwent a phase of exponential, faster-than-light expansion. Think of it not as an explosion into space, but as a sudden, violent stretching of space itself. In this model, the entire observable universe we see today was once a tiny, subatomic speck, a region so incredibly small that every part of it was in intimate contact. This entire region had ample time to even out its temperature, to become perfectly homogeneous before inflation violently blew it up to a macroscopic size in an instant. After this incredible burst of growth, the universe continued expanding at the more sedate rate we see today. Inflation, therefore, solves the horizon problem elegantly. The universe is uniform because it was once small enough to mix thoroughly before being stretched to its current immense scale. But as with many great solutions in science, this one doesn't come for free. While inflation beautifully explains the uniformity, it also predicts something very specific, that the temperature should be almost perfectly uniform, but not quite. The same quantum fluctuations that were present in that tiny seed would have been stretched across the cosmos, creating the tiny, millionth of a degree variations in the CMB that we see as the seeds for all the structure in the universe, the galaxies, stars, and planets. Yet, the very mechanism of inflation, what triggered it, what kind of energy field drove it, and why it stopped remains one of the deepest puzzles in cosmology. It's a solution that works so well we've largely adopted it, but it pushes our understanding of physics into realms we can only theorize about, leaving us to wonder if we've explained a mystery only to uncover an even deeper one. But if the horizon problem presents a puzzle of connectivity, the next mystery confronts us with a startling absence. Our universe is filled with electric charges. Positive protons and negative electrons are fundamental building blocks of matter. Magnets, however, seem to play by a completely different set of rules. Every magnet you've ever held, from a simple refrigerator magnet to the Earth itself, is a dipole. It has a north pole and a south pole. Break a magnet in half and you don't get isolated poles, you simply get two smaller magnets, each with its own north and south. This duality seems to be an unbreakable law of nature, but our most ambitious theories of physics suggest this wasn't always the case. They predict the existence of a truly exotic particle, a magnetic monopole. Think of it as a particle that is a pure north pole without a south, or a pure south pole without a north, a solitary, fundamental magnetic charge. The reason for this prediction lies in what physicists call grand unified theories, or GUTs. These theories represent a monumental effort to describe the fundamental forces of nature as different manifestations of a single, primordial superforce. In the unimaginable heat and density of the very first moments after the Big Bang, the electromagnetic force which gives us light and chemistry, and the strong nuclear force which binds atomic nuclei together, are thought to have been perfectly unified. As the universe expanded and cooled, it underwent a series of cosmic phase transitions, much like steam condensing into water or water freezing into ice. It is during these transitions that grand unified theories predict something remarkable would have occurred: defects in the fabric of spacetime itself. And one of the most dramatic of these defects would be magnetic monopoles. These particles wouldn't be just rare curiosities. The math suggests they should have been produced in staggering abundance, a relic so common that they should be at least as numerous as protons in the universe today. We should be tripping over them, yet despite decades of searching with incredibly sensitive experiments, not a single confirmed magnetic monopole has ever been found. Their absence is deafening. This is the monopole problem, a profound discrepancy between the predictions of our most elegant theories and the observable reality of our cosmos. If grand unified theories are correct, then where did all the monopoles go? Their sheer weight alone would have dramatically altered the evolution of the universe, potentially causing it to collapse long before galaxies could ever form. The fact that we exist in a universe teeming with galaxies and apparently devoid of monopoles is a major clue that our picture of the early universe is missing a crucial piece. Once again, the theory of cosmic inflation emerges as a potential savior. Just as inflation can explain the uniformity of the cosmos, it also provides a neat solution to the monopole dilemma. The idea is that these monopoles were indeed created, but they were formed during that initial, unified phase before inflation began. Then, the universe underwent its fantastic exponential expansion. This sudden stretching would have diluted the density of these primordial relics to an almost unimaginable degree. Imagine you had a single grain of sand in a small box. Now, imagine instantly inflating that box to the size of our entire solar system. The chance of you ever finding that one specific grain of sand becomes infinitesimally small. Inflation does exactly this to the universe. It takes the dense soup of monopoles predicted by grand unified theories and spreads them so thinly across the vastness of space that the probability of one ever wandering into our detectors becomes virtually zero. So, the absence of monopoles isn't evidence against grand unified theories. Instead, it might be the very signature that a period of inflationary expansion actually occurred, effectively sweeping the cosmic stage clean of these exotic particles and allowing the universe we know to take shape. Following the puzzle of missing monopoles, we encounter a mystery that deals with the very shape of reality itself, a question of cosmic geometry known as the flatness problem. To understand this, we need to think about the ultimate fate of the universe. According to Einstein's theory of general relativity, the large-scale geometry of the cosmos is dictated by its density. There are three primary possibilities. The universe could be closed, like the surface of a sphere, with enough matter and energy to eventually halt its expansion and pull everything back together in a big crunch. Alternatively, it could be open, curved like a saddle, destined to expand forever at an ever-increasing rate, with galaxies ultimately drifting apart into cold, isolated darkness. Or there is a third, razor's edge possibility. The universe could be perfectly flat, balanced precariously between these two extremes, expanding forever but at a rate that asymptotically approaches zero. Scientists describe this balance with a parameter called omega, which represents the ratio of the actual density of the universe to the critical density required for flatness. If omega is greater than 1, the universe is closed. If it's less than 1, it's open. If omega equals exactly 1, the universe is flat. Now, here is where the mystery deepens. Through meticulous observations of the cosmic microwave background and the large-scale structure of the cosmos, we have measured omega with incredible precision. The result is startling. Omega is so incredibly close to 1 that the universe appears to be geometrically flat to within a margin of error of just a fraction of a percent. This observed flatness, however, presents a monumental fine-tuning problem when we project it backwards in time. The equations of cosmology show us that any deviation from perfect flatness, any tiny initial value of omega that was not exactly 1, would have been wildly amplified over billions of years of expansion. If the early universe had been even slightly open or closed, that curvature would have grown exponentially. For omega to be so exquisitely close to 1 today, some 13.8 billion years after the Big Bang, it must have been unfathomably closer to 1 in the first moments of existence. The required fine-tuning is beyond staggering. It's been compared to balancing a pencil perfectly on its tip for billions of years, or launching a rocket with such perfect aim that it orbits a distant star millions of light years away. The odds of this happening by random chance seem astronomically low, suggesting that the initial conditions of our universe were set with an almost impossible precision. This is where, for a third time, the theory of inflation provides a powerful and elegant explanation. The The period of hyperfast expansion doesn't just smooth out temperatures and dilute monopoles, it also has a profound effect on the geometry of the universe. Think of the observable universe as the surface of a balloon. Before inflation, this surface could have had any arbitrary curvature. It could have been wrinkled, bunched up, or highly curved. But when you inflate a balloon to an enormous size, a small patch of its surface begins to appear flatter and flatter. Whether you start with a slightly bumpy balloon or a very curved one, inflating it to the size of a house makes the section you're looking at seem perfectly flat. Inflation does this to the cosmos. It takes a potentially highly curved, small region of the primordial universe and stretches it to such an immense scale that any curvature becomes undetectable within our observable horizon. The universe appears flat for the same reason the Earth appears flat when you stand in a field. You're only seeing a tiny, local patch of a much larger structure. Inflation, therefore, predicts a flat universe as a natural consequence of its mechanism, turning a seemingly impossible coincidence into an expected outcome. This solution, however, once again pushes the ultimate question back a step. What was the nature of the inflattened field that drove this process, and why did it produce a universe so exquisitely tuned for the existence of galaxies, stars, and life itself? Having explored the grand cosmic geometry set by inflation, we now turn to the intricate details written onto the canvas of the CMB itself. While inflation elegantly explains the large-scale smoothness of the universe, it simultaneously provides the mechanism for its own beautiful imperfection. This brings us to the fourth mystery, the origin of the primordial fluctuations. Those tiny millionth of a degree variations in the temperature of the cosmic microwave background are not merely static. They are the cosmic DNA, the blueprints from which every galaxy, star, and planet would eventually form. Without these faint ripples, the universe would have remained a vast, featureless sea of gas, forever dark and devoid of structure. The question is, what was the source of these all-important seeds? The leading theory takes us back to the inflationary epoch and into the bizarre realm of quantum mechanics. In the unimaginably dense and energetic environment of the universe's first fraction of a second, even the vacuum of space was not truly empty. According to quantum theory, empty space is a seething foam of virtual particles, constantly flickering in and out of existence. These are quantum fluctuations, tiny, transient variations in energy that happen on the smallest possible scales. Normally, these fluctuations are ephemeral, appearing and vanishing far too quickly to have any lasting effect. But inflation changes everything. As the universe underwent its period of hyper-fast expansion, these fleeting quantum fluctuations were caught in the act and stretched to astronomical proportions. Imagine a tiny, subatomic ripple on the surface of a pond. Now, imagine the pond itself suddenly expanding faster than the speed of light. That tiny ripple would be frozen and magnified, imprinted onto a now gigantic landscape. This is precisely what inflation did. The microscopic quantum jitters in the inflattened field, the mysterious energy field driving the expansion, were amplified and stretched across the cosmos. When inflation ended, these magnified quantum fluctuations were translated into minuscule variations in the density of matter and energy. Slightly denser regions had a stronger gravitational pull, slowly attracting more matter over billions of years, eventually collapsing into the vast cosmic web of galaxies and clusters we observe today. The smooth canvas was given its texture. This theory makes a very specific and testable prediction. If these fluctuations truly originated from quantum processes, their pattern across the sky should follow a particular statistical distribution known as a nearly scale invariant spectrum. This is a sophisticated way of saying that the fluctuations should be present at all scales, from the largest observable distances down to the smallest we can measure, with a similar amplitude. It's a unique fingerprint left by quantum mechanics magnified to a cosmic scale. Incredibly, when satellites like Planck have mapped the CMB with exquisite detail, The pattern of hot and cold spots matches this prediction with remarkable accuracy. This agreement is one of the strongest pieces of evidence we have for the inflationary paradigm, but this success also opens a profound new window into physics. The precise characteristics of these fluctuations, their strength, their distribution, are a direct message from the inflationary epoch, a period of energy so extreme that it is a trillion times beyond what the Large Hadron Collider can probe. By reading the subtle variations in the CMB, we are essentially doing particle physics at energies that will forever be inaccessible to earthly experiments. The cosmic microwave background becomes our ultimate high-energy laboratory, allowing us to test theories about the fundamental forces of nature and the possible unification of quantum mechanics with gravity. Every subtle deviation from the simplest models of inflation provides a clue, hinting at the specific properties of the inflatoned field and the dynamics of the universe in its very first moment. We are deciphering the signature of quantum gravity written in the oldest light there is. This idea of a uniform, isotropic universe, one that looks the same in every direction, is a cornerstone of modern cosmology. It's known as the cosmological principle, and it's the philosophical bedrock upon which we've built our understanding of the cosmos. But what if this fundamental assumption is wrong? What if the universe has a preferred direction, a subtle but real cosmic tilt? This brings us to our fifth mystery, a challenge emerging directly from the CMB data itself, the puzzle of statistical anisotropy. When scientists first mapped the cosmic microwave background, its overall smoothness seemed to be a triumphant confirmation of the cosmological principle. The tiny temperature fluctuations appeared, at first glance, to be randomly scattered across the sky, like a fine, random static. However, as our satellites collected more and more precise data, allowing for incredibly sophisticated statistical analyses, a few peculiar, large-scale patterns began to emerge from the noise. These weren't your typical small hot and cold spots. They were strange alignments and correlations between the largest features in the CMB map. The most famous and controversial of these is a set of correlations that seem to suggest the universe has a preferred axis, a direction that stands out from all others. This alignment has been dramatically nicknamed the axis of evil by researchers, a name that reflects just how disruptive this finding would be if it turned out to be real. So, what exactly are we seeing? The anomalies take a few different forms. One involves the pattern of the fluctuations themselves. In a truly isotropic, random universe, the hot and cold spots should be oriented randomly with respect to each other. But analyzers suggest that the largest scale fluctuations might not be randomly oriented. Instead, their patterns appear to be aligned along a specific direction in space, creating a kind of cosmic preferred plane. Another strange signal involves what's called the quadrupole-octopole alignment. Without getting too deep into the complex math, the quadrupole and octopole are terms that describe specific patterns of hot and cold on the largest scales of the CMB map. In a perfectly random universe, these two patterns should be completely independent of each other. Yet, the data suggests they are curiously aligned, their axes pointing in roughly the same direction. It's as if you tossed a handful of confetti into the air, and instead of it scattering randomly, the pieces all lined up to point north. The implications of a genuine anisotropy are staggering. It would mean that our position in the universe is not entirely ordinary, that there is a special direction on the grandest of scales. This could point to a pre-inflationary structure imprinted on the cosmos, a remnant of a time before the Big Bang that inflation failed to completely erase. Perhaps the universe is not infinite and uniform, but has a more complex topology, like a giant crystal with a repeating pattern on scales larger than we can observe. Or, even more radically, it could suggest that the fundamental laws of physics themselves are not perfectly isotropic, that they vary slightly depending on direction. Any of these possibilities would force a major rewrite of our cosmological textbooks. Before we leap to such revolutionary conclusions, however, we must confront a more mundane possibility, that the axis of evil is not a feature of the universe but a flaw in our perception. The most prominent candidate for such a flaw is something much closer to home, our own galaxy. The Milky Way emits a tremendous amount of microwave radiation that forms a foreground haze, a veil that we must carefully subtract from the data to see the pristine SIMB behind it. If this foreground removal is imperfect, even by a tiny amount, it could potentially introduce false large-scale patterns into the map. Alternatively, the anomaly could simply be a statistical fluke. When you analyze a massive dataset in countless different ways, you are bound to find some correlations that look significant purely by chance. The real test is whether these signals persist as we gather even more precise data from future observatories. For now, the axis of evil remains an intriguing, unresolved whisper in the data, a tantalizing hint that our universe might be stranger and more structured than our most cherished principles allow. Moving from the large-scale suggestion of a cosmic axis, we find another, more localized anomaly that has captured the attention of cosmologists for nearly 2 decades, a mysterious and immense patch of cold in the cosmic microwave background. While the overall CMB map is a tapestry of subtle temperature variations, this feature, known simply as the cold spot, stands out not for its subtlety, but for its stark departure from the expected cosmic noise. Discovered initially in data from the Wilkinson Microwave Anisotropy Probe, or WMAP, and later confirmed with even greater precision by the Planck satellite, this region in the constellation Eridanus is not just a little bit chilly. It is a colossal expanse of sky, spanning a diameter of nearly 1 billion light-years, with a temperature that dips significantly lower than the surrounding average. The significance of the cold spot lies in its statistical improbability. When cosmologists run simulations of the universe based on our standard model, which includes inflation and dark energy, they can predict the kind of temperature fluctuations we should see. These simulations produce maps filled with hot and cold spots of various sizes, but none of them routinely generate a spot as large and as cold as the one we observe. The probability of such a feature arising by random chance in our standard cosmological model is extremely low, estimated to be less than 2%. This has led many researchers to suspect that the cold spot is not a mere statistical fluke, but a genuine signpost pointing to something unusual in the history of our cosmos. The most straightforward explanation, and the one first pursued by astronomers, involves a colossal cosmic structure lying between us and the CMB. Imagine you're looking at a distant warm light, but between you and that light is a vast dark shadow. This is the idea behind the supervoid hypothesis. A supervoid is not just an empty patch of space. It is an enormous region, vastly larger than a typical galaxy cluster, that contains far fewer galaxies and, crucially, far less matter than the cosmic average. According to Einstein's general relativity, as light travels through such an underdense region, it must climb out of a gravitational well. But since the universe is expanding and dark energy is causing that expansion to accelerate, the gravitational landscape itself is changing over time. This combination of effects leads to a phenomenon called the integrated Sachs-Wolf effect. In simple terms, photons of light lose a tiny amount of energy as they travel through an evolving cosmic void, causing them to appear slightly cooler when they finally reach us. If a supervoid of the right size and emptiness were located along our line of sight to the cold spot, it could, in theory, produce the observed temperature dip. The hunt for this hypothetical supervoid began in earnest. Astronomers scanned the region of the cold spot, mapping the distribution of galaxies. They did find a void, an area with a noticeably lower density of galaxies. However, there was a problem. The void they found, while large, was not nearly large or empty enough to account for the profound coldness of the CMB anomaly. The observed cooling from the integrated Sachs-Wolf effect for a void of that scale would be much smaller than what is measured. It's like finding a small ditch when you were expecting to find the Grand Canyon to explain the shadow on the horizon. The mismatch between the observed underdensity and the required one has led many to conclude that a simple supervoid cannot be the sole culprit, pushing scientists toward more exotic possibilities. When conventional explanations fall short, the door opens to more speculative ideas. One of the most captivating theories suggests that the cold spot could be evidence of a cosmic collision, a bruise on our universe caused by an impact with another universe. This idea emerges from the concept of the multiverse, which is a prediction of certain models of eternal inflation. In this scenario, our universe is just one bubble in a vast, frothing sea of universes, each with its own physical laws. Occasionally, these bubbling universes might collide. If a neighboring universe had bumped into ours in the distant past, the energy released at the boundary of that collision could have imprinted a specific signature on the CMB of our universe. The cold spot, according to this theory, could be the remnant of such an encounter, a cosmic scar left by a brush with an entirely separate reality. While this is a thrilling proposition, it is exceptionally difficult to test or verify with our current observational tools, leaving it in the realm of tantalizing but unproven speculation. Other, less dramatic but still fascinating explanations have been proposed. Perhaps the cold spot is not a single anomaly but a chance alignment of several smaller, colder regions, a spot of spots, that only appears as one giant feature from our particular vantage point. Or it could be a rare manifestation of a non-Gaussian fluctuation, a statistical outlier so extreme that it hints at a small deviation from the perfectly random, Gaussian distribution of fluctuations that is a key prediction of simple inflation models. This would mean that the primordial seeds of structure were not entirely random, but had some slight correlations or patterns that we don't yet fully understand. For now, the cold spot remains an open case file in cosmology. It is a persistent, data-driven mystery that challenges the completeness of our standard model and serves as a powerful reminder that the oldest light in the universe still has secrets to reveal. Now, if a preferred axis and a giant cold spot weren't puzzling enough, the plot thickens with a statistical peculiarity that strikes at the very heart of inflation's predictions. This is the mystery of the lack of large-scale correlation. To grasp this, think of the cosmic microwave background not just as a map of hot and cold spots, but as a complex symphony of sound waves frozen in time. These waves, propagating through the primordial plasma, created a characteristic pattern of peaks and troughs in the temperature variations, a harmonic signature that tells us about the contents and history of the early universe. Our models predict a very specific pattern for how these temperature fluctuations should be correlated with each other across different angular distances on the sky. On small and medium scales, the CMB data matches these predictions with spectacular precision. It's a triumphant confirmation of our standard model, but when we zoom out to the very largest scales, patterns wider than 60 degrees across the sky, encompassing nearly a third of the visible universe, something strange happens. The correlations between temperatures in these vastly separated regions are significantly weaker than our theories say they should be. It's as if the universe's background noise has a missing bass note. The most prominent of these large-scale features is known as the low quadrupole. The quadrupole represents the most basic, egg-shaped distortion of the CMB's temperature field. In a universe that underwent inflation, this quadrupole moment should have a certain expected strength, driven by the same quantum fluctuations that seeded all structure. Yet the quadrupole we observe is curiously muted, almost as if someone turned down the volume on the largest possible vibrations. Why is this so troubling? Because inflation, by its very nature, is supposed to create correlations on all scales. The whole point of the inflationary burst is that it took a tiny, causally connected patch and stretched it to become larger than our entire observable universe. This process should have imprinted correlations even on the grandest angles, linking parts of the sky that would otherwise have never been in contact. The fact that these larger-scale correlations are weaker than expected suggests a potential limit. It's as if the cosmic projector screen has a finite size and we're starting to see its edges. This opens the door to a profound possibility. Perhaps our universe is not infinite. Maybe what we call the universe is actually a finite, though incomprehensibly vast, structure with a specific shape or topology. Imagine the universe not as an endless flat plane, but as a giant, multidimensional analog of a video game world that wraps around on itself. If the universe had a small topology, meaning the fundamental repeating unit is smaller than the observable horizon, then the largest waves in the CMB would be physically unable to fit, leading to a cutoff in the power on those scales, exactly as we seem to observe. It would be like trying to play a deep, low-frequency note in a small room. The room itself doesn't support that wavelength, so the sound is weak and distorted. A finite universe could naturally explain the lack of large-scale correlation. Of course, we must always consider the simplest explanation, a statistical fluke. We have only one universe to observe. When you roll a die, you might get a 6 3 times in a row, not because the die is loaded, but simply due to chance. Our observable universe is, in a sense, a single sample. It is possible that we just happen to live in a patch of a much larger, infinite universe where the large-scale fluctuations are, by random chance, unusually quiet. The statistics are borderline. The anomaly is significant enough to be intriguing, but not so extreme that we can rule out chance entirely. Future experiments that can measure the polarization of the CMB with even greater sensitivity might provide the crucial data needed to distinguish between a cosmic coincidence and a true revolution in our understanding of the cosmos's fundamental shape. Until then, the quietness on the largest scales remains a persistent whisper, hinting that the universe's greatest secrets may be hidden in the things we don't see, in the correlations that are mysteriously absent. Just when we thought the universe was testing our assumptions with a preferred axis and a missing base note, the cosmic microwave background presents us with yet another, perhaps even more direct, challenge to our founding principles. This is the mystery of the hemispherical asymmetry. Picture the CMB sky divided neatly in two, like the halves of an orange. According to the cosmological principle, these two hemispheres should be statistical twins. On average, they should have the same number of hot spots, the same number of cold spots, and the same overall amplitude of temperature variations. They should be, for all intents and purposes, interchangeable. But when scientists perform this exact test, they find something deeply unsettling. One half of the sky appears to be noticeably rougher than the other. The fluctuations in that hemisphere have more power. The hot spots are a fraction hotter and the cold spots a fraction colder on average, compared to their counterparts in the opposite celestial hemisphere. It's as if you took a piece of fine grit sandpaper and compared it to a piece with a slightly coarser grit. One side of the universe simply has more texture. What makes this finding even more intriguing and perhaps more worrying is its alignment. The axis that defines this hemispherical power imbalance doesn't seem to be random. It points in a direction that is remarkably similar to the so-called axis of evil we discussed earlier, and it also aligns closely with the plane of our own solar system. This convergence of anomalies along a similar cosmic direction is a red flag that demands careful scrutiny. Is this a genuine feature of the primordial universe, or is it a phantom created by our own local environment? The implications of each possibility are profound. If the asymmetry is real, it means the universe is not just subtly anisotropic on large scales, it is fundamentally lopsided. The initial conditions of the Big Bang were not perfectly symmetric. One direction was born with more vigorous quantum fluctuations than another. This would force us to abandon the cosmological principle as a strict rule and consider models where inflation operated differently in different directions, or where some pre-Big Bang structure imprinted a fundamental handedness onto the cosmos. The first and most critical step is to rule out a local contamination. We are, after all, observing the universe from a moving platform, Earth orbiting the Sun, which is orbiting the center of the Milky Way. Our galaxy emits a fog of microwave radiation that we must meticulously subtract from the data. Could an error in this foreground removal process be creating a false asymmetry? Perhaps interstellar dust or gas in our own galaxy is not perfectly uniform, and a slight miscalibration is leaving a residual signal that makes one half of the CMB sky appear artificially enhanced. Furthermore, the alignment with our solar system's plane is particularly suspicious. It hints at the possibility that something much closer to home within our own cosmic backyard is casting a shadow or adding a signal that we have not fully accounted for. Scientists have developed increasingly sophisticated techniques to model and subtract these foregrounds, and yet the hemispherical asymmetry persists. It stubbornly refuses to be explained away as a simple data processing artifact, which pushes us to consider that we might be seeing something real. Should the asymmetry withstand all these local tests, we are left with truly revolutionary cosmological explanations. One compelling idea connects back to the theory of inflation. What if the inflationary period was not perfectly uniform? Most models assume the inflattened field was the same everywhere, leading to a smooth, isotropic expansion. But what if that field had a gradient? Imagine the field had a slightly higher energy level on one side of the primordial patch than the other. This would mean that inflation ended at slightly different times in different directions. The side with higher energy would have inflated a tiny bit longer, stretching the quantum fluctuations there just a bit more, potentially leading to the observed power imbalance we see billions of years later. This would mean our entire observable universe is just a fragment of a larger asymmetric bubble. Another, even more speculative, idea is that the asymmetry is a sign of our universe brushing up against something else in a multiverse. If our cosmic bubble was even slightly deformed by a near collision with another universe in its infancy, that interaction could have left a permanent mark, a kind of cosmic birthmark that breaks perfect symmetry. For now, the hemispherical asymmetry remains one of the most significant and puzzling anomalies in cosmology. It sits at a frustrating crossroads, too persistent to be easily dismissed as noise, yet not definitive enough to force a paradigm shift. It serves as a powerful reminder that our position as observers is not passive. We must constantly question whether what we see is a true feature of the deep universe or a reflection in our own local mirror. Future observations, particularly of the CMB's polarization, will be crucial. A genuine primordial asymmetry should leave a distinct fingerprint on the polarization patterns, offering a way to finally confirm or refute this cosmic lopsidedness. Until then, it stands as a bold question mark against one of our most deeply held beliefs about the universe, suggesting that the cosmos may not be a perfectly even tapestry, but one with a subtle, fundamental slant. But the peculiarities on the largest scales don't stop with a simple power imbalance. If we zoom in on those very first, most fundamental patterns in the cosmic microwave background, we find an even more specific and baffling arrangement. This is the mystery of the alignments of the low multipoles. To understand what that means, think of the CMB not as a random collection of spots, but as a complex waveform that can be broken down into its constituent harmonics, much like a musical chord can be separated into its individual notes. These harmonics are called multipoles. The lowest multipoles represent the simplest, broadest possible patterns across the entire sky. The dipole is the first harmonic, a simple hot pole and a cold pole, which is mostly caused by our own motion through the universe. The next one is the quadrupole, which describes a basic four-lobed pattern like a clover leaf. Then comes the octopole, an 8-lobed, more complex shape. These are the universe's base notes, the fundamental vibrations that define its largest scale structure. The astonishing finding is that these two separate patterns, the quadrupole and the octopole, are not oriented randomly with respect to each other as our standard cosmological models would predict. Instead, their axes are curiously aligned. It's as if you took two differently shaped cookies, one cloverleaf and one with 8 petals, and found that when you dropped them on a table, they consistently landed with their main features pointing in the exact same direction. This alignment is peculiar enough, but the plot thickens considerably when we look at where this shared axis points. This preferred plane of alignment for the largest features in the entire observable universe coincides remarkably well with the ecliptic plane of our own solar system, the flat disk in which the Earth and other planets orbit the Sun. The chance of such a specific alignment happening randomly is incredibly small, raising a profound and unsettling question. Are we seeing a true feature of the cosmos, or is our local environment somehow contaminating our view of the deepest universe? This alignment is so strange and so potentially disruptive to the cosmological principle that it earned the nickname, the axis of evil, from cosmologists. The name reflects the deep philosophical problem it presents. If the largest structures in the universe are aligned with the plane of our petty little solar system, it suggests a terrifying possibility that we are, in some fundamental way, at the center of the universe. This is a Copernican nightmare, a throwback to a pre-scientific era where humanity placed itself at the heart of creation. The entire edifice of modern cosmology is built on the idea that we occupy no special place, that the universe is homogeneous and isotropic. A genuine alignment with our ecliptic would shatter that assumption, forcing a radical rethinking of everything. Unsurprisingly, the primary suspect in this mystery is not the universe but ourselves. The most likely explanation is a systematic error. We observe the CMB through a veil of foreground emissions from our own galaxy and solar system. The Milky Way's disk creates a bright band of microwave light across the sky that we must meticulously subtract. Even tiny, unaccounted-for anisotropies in this foreground, slight variations in the dust or gas density in our solar system's own neighborhood, could potentially imprint a false pattern on the cleaned CMB map, creating an artificial alignment that just happens to match our ecliptic. Scientists have developed incredibly complex algorithms to peel away these local layers, but the possibility remains that a subtle flaw in this data processing is generating this cosmic mirage. The fact that the alignment is with our solar system plane is the biggest red flag for a local contaminant. However, despite intense scrutiny and repeated attempts to explain it away, the alignment has proven stubbornly persistent across different datasets from different satellites. This resilience forces us to at least entertain the possibility that the signal is real. If it is, the implications are staggering. One theory suggests it could be evidence of a non-trivial topology of the universe. Perhaps the universe is not infinite, but has a finite, multiply-connected shape like a hall of mirrors. If the fundamental cell of this universe was shaped in a certain way, it could impose a preferred plane on the largest observable scales, and by a bizarre coincidence, that plane aligns with our own. Another, even more mind-bending idea is that this alignment is a relic from a pre-Big Bang era, a fossil of some primordial structure or field that dictated the initial conditions of our cosmic bubble. Whatever the true cause, the alignment of the low multipoles remains one of the most tantalizing and unresolved puzzles in cosmology, a whisper of something deeply strange, either about the universe itself or about our unique perspective within it. So far, the anomalies we've encountered have dealt with the size, power, and alignment of features in the cosmic microwave background. But our 10th mystery takes us into an even more subtle realm of statistics, challenging the very nature of the randomness we assume created the universe. This is the search for non-Gaussianity, To grasp this concept, let's step away from the cosmos for a moment and consider something more familiar: a bag of marbles. Imagine you have a huge bag filled with marbles of different sizes, but their sizes follow a very specific and predictable pattern known as a Gaussian or bell curve distribution. If you reach in and grab a handful, you'll most likely get marbles that are all around the average size. Every once in a great while, you might pull out a single marble that's incredibly large or incredibly small, but the chances of grabbing two of these extreme marbles together in the same handful are astronomically low. In a Gaussian system, outliers are not only rare, but they are also completely independent of each other. There are no secret connections between the marbles. This is precisely the statistical assumption that underpins our simplest and most elegant models of inflation. The quantum fluctuations that were stretched across the cosmos are predicted to be Gaussian. The hot and cold spots in the CMB should be like that bag of marbles. The vast majority of temperature variations should be mild and typical, with a few rare, extreme cold spots or hot spots scattered randomly and independently across the sky. There should be no hidden relationships, no subtle correlations that link a particularly large cold spot to a specific arrangement of smaller hot spots nearby. If the fluctuations are Gaussian, it tells us that the physics of inflation was remarkably simple, driven by a single, smooth energy field undergoing a straightforward process. But what if the primordial seeds were not so perfectly random? What if, when we analyze the CMB map with incredibly sophisticated statistical tools, we find hints that the marbles have hidden alliances? This is the essence of non-Gaussianity. It would mean that the fluctuations contain subtle correlations. Perhaps large-scale underdensities have a tendency to be surrounded by a specific pattern of smaller-scale overdensities. Or maybe the distribution of temperature variations has fatter tails than a bell curve would allow, meaning those extreme cold spots, like the one we discussed earlier, are not as rare as they should be, hinting that the underlying process had a tendency to produce more outliers. Finding non-Gaussianity would be like discovering that the universe's quantum dice are ever so slightly loaded. The reason this search is so critical is that it acts as a powerful discriminator between different models of the very early universe. The simplest, most minimal models of inflation, which involve just a single quantum field slowly rolling down a potential energy hill, predict a level of non-Gaussianity that is immeasurably small, effectively perfect Gaussianity. If we were to detect a significant signal, it would immediately rule out a whole class of these elegant, straightforward theories. Instead, it would point us toward more complex and exotic physics at work during inflation. For instance, it could be evidence that inflation was not driven by one field, but by multiple fields interacting with each other in a cosmic dance. The collisions and interactions between these fields could have imprinted those telltale correlations into the fabric of spacetime. Alternatively, it might suggest that the inflattened field itself had a more complicated structure, perhaps with features in its energy landscape that caused it to bump or jerk during its roll, creating non-Gaussian signatures. So, what have we found after decades of painstaking analysis with satellites like Planck? The current consensus is that the CMB is consistent with Gaussianity. The data shows no convincing, statistically significant evidence for non-Gaussian correlations. On one hand, this is a triumph for the simplest models of inflation. The universe, at first glance, appears to have been born from a process of sublime simplicity. But this null result is itself a profound piece of information. It places extremely tight constraints on what kind of inflation could have occurred, effectively ruling out many of the more convoluted and baroque theories. However, the hunt is far from over. The absence of evidence is not evidence of absence. The signals scientists are looking for are exquisitely faint, buried deep within the noise of the measurements. Future observatories, particularly those designed to map the polarization of the CMB with unprecedented precision, will have the sensitivity to probe for levels of non-Gaussianity that are currently beyond our reach. Even a tiny, barely detectable signal would send shockwaves through theoretical physics, forcing a major shift in our understanding of the universe's first moment. The quest for non-Gaussianity is a perfect example of how cosmology progresses. By testing the most fundamental assumptions about randomness itself, we are searching for the hidden handwriting of physics that operated at energies so high they will forever be beyond the reach of any earthly particle accelerator. Now, shifting our focus from patterns and alignments on the sky, we turn to a mystery that deals not with the map of the CMB, but with the very color of its light. This is the puzzle of spectral distortions. The cosmic microwave background radiation is famous for having what is, to an astonishing degree of precision, a perfect blackbody spectrum. What does that mean? Imagine a theoretically perfect object that absorbs all radiation that hits it and then re-emits that energy with a specific, predictable distribution of colors or wavelengths, depending only on its temperature. A hot piece of iron glows red, then orange, then white as it heats up. That's a rough blackbody spectrum. The CMB is the glow of the entire universe, cooled to just 2.7 degrees above absolute zero, and its spectrum matches the prediction for a blackbody of that temperature more perfectly than anything we can create in a laboratory. It is, in fact, the most perfect blackbody ever measured in nature. This near perfection is a direct consequence of the universe's hot, dense, and incredibly uniform beginning. In the first few 100,000 years, the cosmos was a seething plasma of protons, electrons, and photons, all constantly colliding. These countless collisions kept everything in a state of thermal equilibrium, efficiently smoothing out any irregularities in the energy distribution and forcing the radiation into that ideal blackbody curve. The moment the universe cooled enough for atoms to form and the plasma to clear, the photons were set free, their spectrum frozen in time as a pristine snapshot of that equilibrium state. But here's the catch: our theories suggest this perfection shouldn't be quite so absolute. They predict that there should be incredibly tiny, almost imperceptible deviations from this perfect blackbody curve, minute spectral distortions etched into the light like faint watermarks. Why would these distortions exist? They are the ghosts of events that happened either just before the CMB was released or long after, events that injected energy into the cosmic bath and subtly ruffled its smooth surface. One major source is thought to be the dissipation of sound waves in the primordial plasma. In the first few 100,000 years, the universe was ringing like a bell from the initial quantum fluctuations. These sound waves traveling through the plasma would have eventually dissipated their energy through a kind of friction, slightly heating the photon gas. This process, if it occurred after the universe was about 100,000 years old, would not have had enough time to be fully smoothed out by collisions before the photons decoupled. The result would be a specific type of spectral distortion known as a mu distortion, a tiny bump in the spectrum at certain wavelengths. Other potential causes are even more exotic and thrilling. The decay of hypothetical, unknown particles from the very early universe could have dumped significant energy into the primordial plasma. Imagine a population of massive particles, relics from a grand unified epoch, slowly decaying and releasing their mass energy as radiation. This sudden injection of energy would have disturbed the thermal equilibrium, leaving a distinct fingerprint. Similarly, the evaporation of primordial black holes, tiny black holes that may have formed from extreme density fluctuations in the first second of the Big Bang, could be another source. As these black holes lose mass through Hawking radiation, they would ultimately explode in a final burst of energy, creating a localized but potentially detectable spectral distortion. Finding such a signal would be direct evidence for phenomena that are currently entirely theoretical. The challenge, of course, is that these distortions are predicted to be incredibly small. We're talking about deviations of just a few parts in a billion or even a trillion from the perfect blackbody curve. Our current satellites like COBE and Planck, which confirm the blackbody nature of the CMB with magnificent precision, simply weren't sensitive enough to detect distortions at this minute level. They've told us what the perfect canvas looks like, but they couldn't see the faint, ghostly brushstrokes layered on top. This is where the future of cosmology gets incredibly exciting. Proposed missions like the Primordial Inflation Explorer or PIXIE are designed specifically for this hunt. PIXIE would be a spectrometer of unparalleled sensitivity, capable of measuring the CMB's spectrum across a wide range of frequencies with an accuracy hundreds of times greater than previous instruments. Discovering even the faintest spectral distortion would open an entirely new window into cosmic history. It would be like finding a hidden diary entry from a time before the cosmic microwave background picture was taken. A mu distortion would give us a precise timestamp for when energy was injected, telling us about the physics of the universe during its infancy. A signal from particle decay or primordial black holes would be a direct probe of physics at energy scales so high they are forever beyond the reach of particle colliders on Earth. These spectral fingerprints are therefore more than just tiny anomalies. They are potential messages from the darkest and most poorly understood chapters of the universe's story, waiting for a sensitive enough instrument to finally listen. Moving beyond the spectrum of the light itself, we come to a mystery that many cosmologists consider the ultimate prize in observational cosmology, a potential window directly into the first sliver of a second after the Big Bang. This is the quest for B-mode polarization in the cosmic microwave background. To understand why this is so important, we need to first grasp what polarization means in this context. The light from the CMB is not just a simple glow, it's made of photons that have a specific orientation, a property we call polarization. Think of light as a wave vibrating in a particular direction. When this light scatters off particles, like the electrons in the primordial plasma just before the CMB was released, it acquires a preferred orientation, much like sunlight reflecting off the surface of a lake becomes polarized, creating glare. This process imprinted a specific curling pattern on the CMB light, known as E-mode polarization. This pattern is primarily caused by density fluctuations in the early universe, the same sound waves that created the hot and cold spots. Scientists have already detected this E-mode signal with great precision, and it beautifully confirms our picture of the primordial plasma. But there's another, far more elusive type of polarization predicted by theory, B-mode polarization. If E-modes are curly patterns, B-modes are a swirly, twisting pattern on the sky. This subtle distinction is everything. While E-modes are generated by the relatively tame physics of matter clumping together under gravity, B-modes are believed to be the unique signature of something far more profound, primordial gravitational waves. Gravitational waves are ripples in the very fabric of spacetime itself, first predicted by Einstein over a century ago and directly detected for the first time in 2015 from the collision of black holes. But the waves generated by such astrophysical events are mere ripples in a pond compared to the cosmic tsunami we're talking about here. Primordial gravitational waves would have been generated by the most violent event in history, the inflationary burst. As the universe underwent that fantastic, faster-than-light expansion, the intense gravitational turmoil would have sent shockwaves reverberating through the structure of spacetime. These waves would have been literally frozen into the cosmos as it expanded, and their passage would have gently tugged on the primordial plasma, imparting a distinct, swirling B-mode pattern onto the polarization of the CMB photons. Detecting this signal is the holy grail because it would be a direct probe of inflation at energy scales 1 trillion times higher than what we can achieve in particle accelerators. The strength of the B-mode signal is directly tied to the energy scale at which inflation occurred. A detection would tell us not just that inflation happened, but how it happened, how powerful it was, and by extension, what kind of exotic physics drove it. It would be our first and only direct observational link to the Planck epoch, a time when gravity itself was thought to be quantum in nature. For this reason, the search for primordial B modes has become one of the most intense and high-stakes endeavors in all of science. This intensity reached a fever pitch in March of 2014 with the announcement from the BICEP-2 collaboration, a specialized telescope located at the South Pole. The team reported with great fanfare that they had detected the long-sought B-mode polarization, a finding that was immediately hailed as potentially Nobel Prize winning. The excitement was palpable. It seemed we were on the verge of directly witnessing the birth of the universe. However, that excitement was short-lived. A crucial complication soon emerged. Our own Milky Way galaxy is filled with interstellar dust, and this dust, when aligned by magnetic fields, can also emit polarized light that mimics the swirling pattern of primordial B modes. The BICEP-2 team had used the best available models of this galactic dust to subtract its contribution, but the subsequent joint analysis with data from the Planck satellite revealed a sobering truth. The signal they detected was almost entirely attributable to this foreground contamination. It was a cosmic mirage, a heartbreaking case of our own galaxy's dust getting in the way of seeing the dawn of time. The BICEP-2 episode, while a setback, was not a failure. It was a powerful lesson in the extraordinary difficulty of this measurement and served to galvanize the entire field. It highlighted the necessity of multi-frequency observations. Galactic dust glows brightly at certain wavelengths, while the pristine CMB has a very different spectral signature. By observing the sky at many different frequencies simultaneously, modern experiments can meticulously separate the faint cosmological signal from the bright galactic foreground. Today, a new generation of incredibly sensitive experiments is underway, involving arrays of telescopes at the South Pole, in the high Chilean Andes, and even on balloon-borne platforms soaring high above most of Earth's atmosphere. These collaborations are collecting petabytes of data, applying ever more sophisticated analysis techniques to tease out the infinitesimally weak whisper of primordial gravitational waves from the roar of local interference. The challenge is immense. The signal they are hunting for is staggeringly faint, a polarization signal that is perhaps a few tens of nanokelvins in amplitude, a fluctuation smaller than 1 part in 10 million. It is a search for a ghostly signature buried under layers of cosmic noise, yet the potential reward is so profound that the effort continues unabated. A clean, undeniable detection of primordial B modes would arguably be the most significant discovery in cosmology since the CMB itself was found. It would open a completely new branch of astronomy, allowing us to listen to the gravitational echoes of creation and finally test theories about what truly sparked the universe into being. The hunt for this swirling pattern in the oldest light is a testament to our enduring curiosity, a relentless search for a whisper from the very beginning. While the search for primordial B modes captures the imagination, the more common E-mode polarization of the cosmic microwave background holds its own set of intriguing puzzles. Think of E-mode polarization as the fingerprint left by the last interaction between light and matter, a direct result of the sound waves rippling through the hot plasma of the early universe. As those density waves compressed and rarefied the primordial soup, they created a distinct curling pattern in the orientation of the escaping photons. Because this signal is generated by the same density fluctuations that create the temperature variations, we would logically expect the E-mode map to be a close cousin of the temperature map. Its patterns should align, and its statistical properties like the hemispherical power asymmetry or the alignment of large-scale features should echo what we see in the heat map of the cosmos. This expectation turns E-mode polarization into a powerful forensic tool. If a strange feature appears in the temperature map, but then vanishes or looks completely normal in the polarization map, the most likely culprit is a systematic error in our measurements or foreground subtraction. It's a bit like hearing a strange noise in your car. If you only hear it when the air conditioning is on, you suspect the blower motor. But if you hear the same noise with the AC off, with the radio on, and while going over bumps, you start to think the problem is something more fundamental, like the transmission. Similarly, if the mysterious axis of evil or the hemispherical power asymmetry shows up with the same strength and orientation in the independent data of the E-mode polarization, it becomes much harder to dismiss as a simple artifact. It would point strongly toward a genuine, physical anomaly imprinted on the universe at the moment of last scattering, a true feature of the primordial cosmos. The latest data from the Planck satellite and other experiments adds a fascinating layer of complexity to this detective story. When scientists meticulously analyze the E-mode map, they do indeed find hints that some of the temperature anomalies might have a counterpart. The evidence is subtle and not yet conclusive, but there are suggestions that the large-scale power asymmetry, the idea that one half of the sky is rougher than the other, might also be present in the polarization data. This is a profoundly important clue, because the processes that create temperature fluctuations and E-mode polarization are intimately linked but not identical. A persistent signal across both datasets would be a powerful argument that we are seeing a real cosmological effect and not just a ghost in the machine. However, the picture is not perfectly clear. The alignment of the lowest multipoles, the axis of evil that seemed to connect the quadrupole and octupole in the temperature data, does not appear to be as pronounced in the polarization data. This discrepancy is itself a mystery. It could mean that the alignment was in fact a statistical fluke or a residual foreground contamination that was more effectively cleaned from the polarization data. Alternatively, it might indicate that the physics responsible for the alignment operated in a way that affected the density fluctuations differently than the polarization patterns, a nuance that could provide a crucial clue about the mechanism behind the anomaly. The fact that the signals don't match perfectly between temperature and polarization forces us to be even more meticulous in our analysis, reminding us that the universe is under no obligation to make things simple for us. This independent check provided by E-mode polarization is what makes it so valuable. It's a second witness on the stand, corroborating or challenging the testimony of the temperature map. As we continue to refine our measurements, particularly with next-generation CMB experiments that will map polarization with unprecedented sensitivity, the story of these anomalies will undoubtedly become clearer. Either they will fade away, revealed as intricate illusions born from the immense challenge of observing the universe from within our own galaxy, or they will solidify, forcing a revolutionary reassessment of our standard cosmological model and revealing an early universe that was far more complex and textured than we ever imagined. The story of the cosmos isn't just written in the light of the CMB. It's also encoded in the very atoms that make up our bodies and the world around us. This brings us to a mystery that connects the universe's baby picture directly to its chemical infancy, a puzzle known as the lithium problem. To understand it, we need to travel back to a time even before the CMB was released to the universe's first 3 minutes. This was the epoch of Big Bang nucleosynthesis, or BBN, the incredibly brief period when the entire cosmos was hot and dense enough to act as a nuclear fusion reactor, forging the first atomic nuclei from a primordial soup of protons and neutrons. The theory of BBN is a cornerstone of modern cosmology. It makes very specific predictions about how much of each light element, hydrogen, helium, and trace amounts of lithium and deuterium should have been created. For decades, these predictions were difficult to test with precision because we had a major unknown: the exact density of ordinary matter, also called baryonic matter, in the early universe. Without knowing how many protons and neutrons were in the primordial soup, it was impossible to precisely calculate how many would fuse together to form heavier elements. This all changed with the exquisitely detailed maps of the cosmic microwave background. You see, the tiny temperature fluctuations in the CMB are not just random patterns. Their specific characteristics, particularly the relative heights of the acoustic peaks, are exquisitely sensitive to the density of baryons in the universe at the time the light was set free. By analyzing these peaks, satellites like Planck have given us a highly precise measurement of this density. It's as if the CMB provided us with the final, crucial ingredient for the BBN recipe. With this number in hand, cosmologists can now run sophisticated simulations of the universe's first few minutes with remarkable confidence. The results are, for the most part, a spectacular success. The predicted abundances of deuterium and helium-4 based on the CMB density match the amounts observed in the oldest, most pristine regions of the universe with stunning accuracy. It's a magnificent confirmation that our understanding of nuclear physics and cosmology during this critical epoch is fundamentally correct. But there is one glaring, persistent exception: lithium. The same calculations that so perfectly predict deuterium and helium tell us that the universe should contain about 3 times more lithium-7 than we actually observe. Astronomers measure the lithium abundance in the atmospheres of the oldest stars in our galaxy, stars that formed from material that had undergone little chemical processing, and they consistently find this significant shortfall. It's a discrepancy that has stubbornly resisted explanation for decades. We have the right recipe, the right amount of ingredients as measured by the CMB, and yet the final dish is missing a key element. This is the lithium problem, and it hints that something is missing from our picture of the universe's first few minutes. So, what could be going wrong? If the math works perfectly for deuterium and helium, it seems unlikely that our basic understanding of nuclear fusion during BBN is fundamentally flawed. Instead, physicists are exploring the possibility that some new, unknown physical process was at play, subtly altering the nuclear chain reactions that produced lithium. One intriguing idea involves the decay of hypothetical exotic particles that may have been present in the early universe. For instance, certain types of supersymmetric particles could have decayed, injecting high-energy photons or other particles into the primordial soup. These injections could have disrupted the delicate nuclear equilibrium, perhaps by breaking apart the fragile beryllium-7 nucleus, which is the radioactive precursor to lithium-7. By destroying some of this beryllium-7 before it could decay into lithium, the observed abundance could be brought into line with predictions. Another possibility is that our understanding of the nuclear reaction rates themselves needs a slight tweak. The cross-sections, which essentially measure the probability that 2 nuclei will collide and fuse for some of the reactions leading to lithium, are difficult to measure in laboratory experiments on Earth. Even a small revision to these rates, still within experimental uncertainties, could potentially resolve the discrepancy. Or perhaps the universe was not perfectly smooth during BBN. If there were slight inhomogeneities in the density of protons and neutrons, areas with different concentrations could have produced different amounts of elements, and the average we observe today might not match the prediction for a perfectly uniform soup. The significance of the lithium problem cannot be overstated. While it might seem like a small detail concerning a relatively rare element, it is a potential crack in the otherwise seamless edifice of the standard model of cosmology. It suggests that our knowledge of physics during the first few minutes of the universe, a period we thought we understood quite well, may be incomplete. Solving this puzzle could open a window into physics beyond the standard model of particle physics, revealing the existence of new particles or forces that operated only in the extreme environment of the Big Bang. It's a reminder that even the oldest fossils, whether they are atoms or photons, can still surprise us with messages from the dawn of time. And just as we grapple with a cosmic chemical imbalance in the form of the lithium problem, we encounter a far more pressing crisis that strikes at the very heart of our cosmological model, a discrepancy so significant it has been dubbed the Hubble tension. This isn't just a minor accounting error, it's a fundamental clash between two of our most trusted methods for measuring the universe's current expansion rate, known as the Hubble constant. On one side, we have the cosmic microwave background, the fossilized light from the infant universe. The Planck satellite's incredibly precise map of the CMB allows us to essentially play the movie of the universe backwards. We know the initial conditions from the CMB, we know the ingredients of the universe: dark energy, dark matter, ordinary matter, from the lambda CDM model, and we can run the simulation forward 13.8 billion years to predict what the expansion rate should be right now. This cosmic forensics points to a Hubble constant of about 67.4 kilometers per second per megaparsec. This means that for every megaparsec, a distance of about 3.26 million light-years, a galaxy is moving away from us at 67.4 kilometers per second faster. But when we turn our telescopes to the present-day universe and measure the expansion rate directly using what's called the distance ladder, we get a different answer. This method relies on observing nearby galaxies and using brilliant cosmic mile markers like Cepheid variable stars and Type 1a supernova. These are standard candles, objects whose intrinsic brightness we know, allowing us to calculate their distance precisely. By measuring both the distance to a galaxy and its velocity from the redshift of its light, we can directly measure the Hubble constant. Teams using the Hubble Space Telescope and other observatories have consistently found a value around 73.0 kilometers per second per megaparsec. The difference, about 5.6 kilometers per second per megaparsec, might sound small, but the uncertainty in each measurement is now so tiny, less than 2%, that the gap between them is statistically significant. They are fundamentally incompatible. It's as if you calculated how fast a car should be going based on the power of its engine and the incline of the road, and got one answer, but then pointed a radar gun at it and got a noticeably different speed. One of our most basic understandings of the cosmos is being directly challenged. The implications of this tension are profound, and the CMB is right at the center of the storm. The first and most conservative possibility is that there is an unaccounted for systematic error in one or both sets of measurements. Perhaps our calibration of the cosmic distance ladder is subtly off. Maybe there's something we don't understand about the physics of Cepheid variables or supernova in the nearby universe that is skewing the local measurement. Alternatively, the Planck data could have some unmodeled contamination, though scientists have scrutinized it relentlessly. However, as the measurements have become more and more precise over the last decade, the discrepancy has not gone away. If anything, it has solidified. This persistent tension is what leads many cosmologists to suspect that the issue isn't a measurement error, but a flaw in the cosmological model itself. The lambda CDM model, which has been so successful in describing the universe, might be missing a crucial ingredient. This is where the excitement truly begins, because the hunt for new physics is on. One of the leading candidates is the idea of early dark energy. In our standard model, dark energy, the mysterious force causing the universe's expansion to accelerate, is a recent phenomenon, only becoming dominant in the last few billion years. But what if a small amount of this exotic energy was also active in the very early universe, just before the CMB was released? This early dark energy would have subtly changed how sound waves propagated in the primordial plasma, altering the precise sizes of the acoustic peaks in the CMB that Planck measured. This tweak would, in turn, change the predicted value for the Hubble constant when we run the cosmic simulation forward, potentially raising it to align with the local measurements. Early dark energy acts as a temporary cosmic booster rocket, giving the early universe an extra nudge that changes its entire evolutionary trajectory. Other exotic proposals are also on the table. Perhaps neutrinos, the ghostly particles that stream through the universe almost unnoticed, are not what we think they are. If they have exotic properties like being able to interact with each other or with dark matter in ways not included in the standard model, they could have influenced the expansion history. Or maybe dark energy isn't a constant but is dynamically evolving over time. Another fascinating, though more speculative, idea is that our local region of the universe is not entirely representative. We might be living in a vast cosmic void, a region of slightly lower density than the cosmic average, which could affect our local measurement of the Hubble constant, making it appear faster than it truly is for the universe as a whole. The Hubble tension is more than just a number puzzle. It is a direct confrontation between our view of the ancient universe as seen in the CMB and our view of the contemporary cosmos. The CMB gives us a single, frozen snapshot from the dawn of time, and from it we extrapolate a history. The local measurements give us a direct look at the present-day expansion rate. The fact that these two powerful, independent methods disagree is a clear signal that our extrapolation, our standard model of cosmology, is incomplete. Resolving this tension is arguably the single most important goal in cosmology today, because the solution, whatever it may be, promises to reveal a deeper layer of reality, perhaps introducing us to a new force or particle that has been shaping the destiny of the cosmos all along. While the Hubble tension captures headlines with its direct clash over the universe's expansion speed, a quieter but equally significant discord has been growing in the background, one that deals not with how fast the cosmos is growing, but with its internal architecture. This is the mystery of the sigma-8 tension, and it challenges our understanding of how the universe's vast cosmic web of galaxies and clusters actually formed. If the Hubble constant tells us about the engine of expansion, the parameter sigma-8, often written as S8, tells us about the blueprint, the predicted lumpiness of matter on the largest scales. Think of it this way: the initial quantum fluctuations imprinted on the CMB were the seeds, and the combined forces of gravity, dark matter, and dark energy acted as the weather that determined how those seeds would grow into the grand structures we see today. The process is relatively straightforward in our standard model. Slightly denser regions in the early universe, revealed by the hotspots in the CMB, had a stronger gravitational pull. Over billions of years, they drew in more and more dark matter and ordinary matter, eventually collapsing into the filaments, clusters, and superclusters that make up the cosmic web. The precise pattern of these initial fluctuations, as measured by Planck, allows cosmologists to make a very specific prediction for how much structure should exist in the universe right now. This prediction is quantified by the S8 parameter. A higher S8 value means a more clumpy universe with matter more concentrated into dense knots. A lower value suggests a smoother, more evenly distributed cosmos. Based on the pristine CMB data, the standard model predicts an S8 value of around 0.81. The tension arises when we try to measure this clumpiness directly in the local, evolved universe. Instead of looking at the ancient light of the CMB, astronomers use techniques that probe the distribution of matter as it exists today. One of the most powerful methods is weak gravitational lensing. As light from distant galaxies travels across the cosmos to reach us, its path is subtly bent by the gravitational influence of all the matter, both light-emitting and dark, that it passes along the way. This bending distorts the shapes of those background galaxies in a specific statistical way. By carefully measuring the tiny, coherent distortions in the shapes of millions of galaxies, surveys like the Dark Energy Survey and the Kilo-Degree Survey can essentially create a three-dimensional map of the total matter distribution, revealing its inherent lumpiness. Another method involves counting galaxy clusters. The number of massive clusters in a given volume of space is extremely sensitive to the S8 parameter. A clumpier universe will naturally form more and larger clusters. The results from these direct, late-universe measurements are consistent with each other, but they are in clear tension with the CMB-based prediction. They suggest an S8 value that is lower, around 0.76. The universe, according to these observations, appears to be about 5 to 10% smoother, less clumpy than our standard model says it should be after 13.8 billion years of growth. This isn't a huge discrepancy, but like the Hubble tension, the uncertainties have shrunk to the point where it's hard to dismiss as simple chance. It's as if you planted a garden based on a specific seed packet, carefully followed the growing instructions, but when you came to harvest, the plants were consistently and noticeably less bushy than expected. The blueprint and the final construction don't quite match. So, what could be causing this apparent lack of structure? One leading hypothesis points to the mysterious properties of dark matter. In our standard model, dark matter is cold and collisionless. This means its particles move slowly compared to the speed of light, and they mostly pass right through each other and ordinary matter without interacting, feeling only the force of gravity. This simplicity is what allows it to efficiently clump together and form the gravitational scaffolding for galaxies. But what if dark matter has a small amount of intrinsic interaction? If dark matter particles could bump into each other or interact with a dark force, this would create a kind of internal pressure that would resist gravity's pull, preventing matter from collapsing into quite as dense structures. This self-interacting dark matter would naturally lead to a smoother cosmic web, potentially explaining the lower S8 measurements. It's a tantalizing idea that is actively being explored through both simulations and astronomical observations. Another possibility involves the other great cosmic mystery, dark energy. In our standard model, dark energy is a constant force, its strength not changing over time. But if dark energy began to influence the universe earlier than we think, or if its strength has been slowly increasing, it could have acted to suppress the growth of structure. As dark energy drives the accelerated expansion of space, it makes it harder for gravity to pull matter together. If this anti-gravity effect became significant a few billion years earlier than our models assume, it could have put the brakes on structure formation just enough to result in the slightly smoother universe we seem to observe. This would connect the sigma-8 tension directly to the Hubble tension, as a dynamical dark energy could potentially address both problems simultaneously, making it an extremely attractive area of theoretical research. Of course, we must also consider the more mundane explanation, that our measurements of the local universe's clumpiness are systematically biased. Mapping the cosmic web through weak lensing is an astronomically complex task. It requires understanding the intrinsic shapes of galaxies, calibrating telescope optics to incredible precision, and modeling subtle effects like the alignment of galaxies due to their local environment, which can mimic a lensing signal. While teams have gone to great lengths to account for these potential biases, the possibility remains that an unaccounted for systematic error is making the universe appear smoother than it truly is. The fact that different late universe probes, like lensing and cluster counts, seem to agree on a lower S8 value strengthens the case for new physics, but it doesn't entirely rule out a common, hidden flaw in our observational techniques. The sigma-8 tension may be less famous than its Hubble counterpart, but its implications are just as profound. It probes a different aspect of our cosmological model, the growth of structure rather than the expansion history. A genuine discrepancy here would force us to revise our understanding of the dark sector of the universe, suggesting that either dark matter is not entirely passive or that dark energy is more dynamic than a simple cosmological constant. As new, even more powerful telescopes like the Vera-C, Rubin Observatory come online, they will map the distribution of matter across the sky with unprecedented detail, providing a definitive measurement of S8. The outcome of this quiet tension will determine whether our standard model needs a minor adjustment or a major overhaul, revealing whether the dark components of the cosmos are simpler or far more complex than we ever imagined. But the cosmic tensions over expansion and clumpiness inevitably lead us to a deeper, more fundamental question about the invisible substance that dictates the universe's structure. What exactly is dark matter? The cosmic microwave background provides our most powerful and direct window into its essential nature. While we cannot see dark matter directly, its gravitational influence left an indelible mark on the oldest light in the universe, a signature we can decode by examining the precise pattern of the CMB's acoustic peaks. These peaks are not just a random collection of hills and valleys on a graph. They are the frozen record of sound waves sloshing back and forth in the primordial plasma, and their relative sizes and positions tell a detailed story about the ingredients of the cosmic soup. To understand how this works, picture the early universe as a fluid made of three main components: photons, which are particles of light; baryons, which are ordinary matter like protons and neutrons; and dark matter. In the first few 100,000 years, these components were tightly coupled. The photons exerted an immense outward pressure, like a powerful radiation wind, while gravity tried to pull the baryons inward. This created a tug-of-war, causing the plasma to oscillate in standing waves. But dark matter played a uniquely critical role in this cosmic symphony. Because it does not interact with light or ordinary matter except through gravity, dark matter was immune to the intense radiation pressure. It simply sat there, forming stable gravitational wells from the very beginning. These dark matter wells acted as an anchor. They provided a foundation for the baryons and photons to clump around, enhancing the gravitational pull and making the oscillations more pronounced. The result of this interaction is etched into the CMB power spectrum. The height of the first acoustic peak, in particular, is a direct measure of the total density of matter in the universe, with dark matter making up the overwhelming majority. The ratio of the heights of the second and third peaks is especially telling. The second peak is sensitive to the density of baryons, the more ordinary matter present. The more it resisted the gravitational collapse due to photon pressure, suppressing this peak. The third peak, however, is a measure of the density of dark matter. Its robustness tells us that a dominant gravitating substance was present that was completely unaffected by the radiation, allowing structures to begin forming even before the CMB was released. The exquisite data from Planck shows a third peak that is strong and clear, providing overwhelming evidence for the existence of a cold, collisionless form of dark matter. This model, where dark matter is cold, meaning its particles moved slowly in the early universe, and collisionless, meaning they pass through each other and everything else without interacting, has become the standard for a very good reason. It fits the CMB data spectacularly well. However, the very precision of the CMB measurement also allows us to search for tiny deviations from this simple picture, to ask whether dark matter might have even the faintest whisper of interaction. What if dark matter particles could, on very rare occasions, bump into each other? Or what if they had a tiny, residual interaction with photons or neutrinos? This idea of self-interacting or slightly warm dark matter is not just a theoretical curiosity. It has profound implications. If dark matter has any internal interactions, it would behave less like a collection of independent particles and more like a fluid with its own pressure. This would affect how it clumps together. On very small scales, this interaction would tend to smooth out dark matter distributions, potentially solving nagging problems in galaxy formation, such as why the centers of some galaxies appear less dense than simulations of cold dark matter predict. The CMB is sensitive to these subtle effects because any interaction would have left an imprint on the largest scales of the power spectrum. If dark matter were warm, meaning its particles were moving at a significant fraction of the speed of light in the early universe, they would have streamed out of small-scale density fluctuations, washing them out. This would suppress the power on small angular scales in the CMB. The fact that we see power on all scales tightly constrains how warm dark matter could be, effectively ruling out models where it is too fast-moving. But the data still allows for a small amount of interaction or a tiny, non-zero temperature. Scientists are therefore meticulously analyzing the CMB data, looking for any slight smoothing or anomalous feature that doesn't quite fit the perfect cold dark matter model. Finding even a hint of such a signal would be a monumental discovery, providing our first clue about the particle physics of dark matter. It would tell us that dark matter is not entirely inert and simple, but part of a richer, more complex dark sector of the universe with its own forces and particles. The silent, shadowy majority of matter in the cosmos may yet have a subtle voice, and we are learning to listen for its faint echo in the first light of creation. But if dark matter represents the invisible scaffolding that holds the cosmic structure together, then dark energy is the mysterious force that is actively pushing it apart. This brings us to our 18th mystery, a force so enigmatic that its true nature remains one of the greatest puzzles in all of science. The cosmic microwave background provides a critical, if indirect, key to unlocking this mystery. To understand how, we need to think about the CMB not just as a snapshot, but as a measuring stick for the entire history of the cosmos. The size of the acoustic peaks in the CMB power spectrum acts as a standard ruler. We know precisely how large these sound waves were in the primordial plasma, a physical scale imprinted by the physics of the early universe. By measuring the apparent angular size of these peaks on the sky today, we can effectively measure the geometry of the universe and how it has expanded between then and now. This is where dark energy enters the picture with dramatic effect. When we combine the CMB's view of the infant universe with observations of the cosmos at intermediate ages, like the distribution of galaxies, and with the local measurement of the Hubble constant, we get a complete timeline of cosmic expansion. The story this timeline tells is startling. For the first several billion years, the expansion of the universe was slowing down, as expected, due to the mutual gravitational attraction of all the matter within it. But then, around 5 to 6 billion years ago, something extraordinary happened. The expansion began to accelerate. It was as if a cosmic repulsive force, previously dormant, suddenly switched on and began to overpower gravity. This accelerating agent is what we call dark energy. The most pressing question, then, is what dark energy actually is. The simplest explanation, and the one that fits the current data remarkably well, is the cosmological constant, an idea first proposed by Albert Einstein and later abandoned as his greatest blunder. In this model, dark energy is an inherent property of the vacuum of space itself. Empty space, according to quantum physics, is not truly empty. It is a seething sea of virtual particles popping in and out of existence. This vacuum energy would have a constant density and exert a negative pressure, causing the expansion of the universe to accelerate. The key characteristic of this cosmological constant is that its equation of state, represented by the parameter W, is exactly equal to -1. This value means that the energy density of dark energy remains constant over time. As the universe expands and new space is created, the density of dark energy does not dilute. This is why it eventually comes to dominate the cosmos. The density of matter falls as the universe grows, but the density of dark energy stays the same. The incredible precision of the Planck CMB data, when combined with other cosmological probes, allows us to measure this W parameter with ever-increasing accuracy. The current results are consistent with W equals -1, the cosmological constant model, for all its puzzling philosophical implications, works. But consistent with is not the same as proven to be. The real excitement in cosmology today lies in the hunt for tiny deviations from this simple picture. Even a minuscule deviation, say W equaling -0.999 instead of -1, would completely revolutionize our understanding of physics. It would mean that dark energy is not a static cosmological constant, but something dynamic that evolves over time. Such a discovery would rule out Einstein's simple vacuum energy and point toward a vast family of theoretical candidates known as quintessence. Quintessence is the name for a class of models where dark energy is not a constant property of space, but a dynamic field that permeates the universe, similar to the inflaton field that may have driven inflation. If dark energy is quintessence, its density and pressure could change over time. The equation of state parameter W could have been different in the past and could continue to evolve in the future. This would open up breathtaking possibilities for the ultimate fate of the cosmos. A cosmological constant leads to a predictable, if lonely, future of perpetual, accelerating expansion. But a dynamical dark energy could lead to wildly different outcomes. It could gradually fade away, allowing gravity to reassert control. Or it could grow stronger and stronger, leading to a catastrophic big rip, where the accelerating expansion becomes so violent that it tears apart galaxies, solar systems, and even atoms themselves in the far future. The cosmic microwave background is our most powerful tool for constraining these possibilities. While the CMB itself originates from a time long before dark energy became important, it sets the initial conditions for the entire cosmic expansion history. By pinning down the amounts of dark matter and ordinary matter with extreme precision, the CMB data effectively reduces the number of free variables in our models. This allows measurements of the universe at later times, such as the distances to supernova or the clustering of galaxies, to provide a much sharper measurement of dark energy's properties. It's like knowing the exact amount of fuel in a rocket's tank at launch. You can then much more accurately calculate the effect of any subsequent thrust. Future CMB experiments, especially those focused on polarization, will work in tandem with next-generation galaxy surveys to measure W with a precision of 1% or better. This concerted effort is a direct assault on the nature of dark energy, a quest to determine whether the force shaping the destiny of our universe is a simple, immutable constant or a dynamic, evolving entity whose secrets are only beginning to be revealed. While dark energy and dark matter dominate the cosmic budget today, the early universe was a much more crowded and energetic place, teeming with relativistic particles moving at or near the speed of light. This brings us to a mystery that connects the grand scales of cosmology directly to the microscopic world of particle physics, a puzzle concerning the precise count of these light-speed inhabitants in the primordial soup. It's a number known as the effective number of neutrino species, or NEFF for short. To grasp its importance, imagine trying to calculate how long it will take a large pot of water to boil. You need to know not just the intensity of the flame, but also the amount of water in the pot. In the early universe, the expansion rate and the cooling timeline are critically dependent on the total density of all this relativistic energy, which includes not only photons but also neutrinos and any other light, fast-moving particles that may have been present. In our well-tested standard model of particle physics, the cast of characters for this relativistic era is quite specific. We have photons, the particles of light, and we have three known types or flavors of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. These neutrinos are ghostly particles that barely interact with matter, but in the hot, dense early universe they were abundant and played a crucial role. Calculations based on this standard model roster predict that the effective contribution of these neutrinos to the energy density should be equivalent to approximately 3.044 species. Why not a neat 3? The number is slightly higher than 3 due to subtle effects from particle physics, such as neutrino oscillations, and the fact that neutrinos were not completely decoupled from the plasma when electrons and positrons were annihilating, which transferred a little extra energy into them. This number, 3.044, is a firm prediction. The cosmic microwave background serves as a cosmic thermometer and chronometer for this epoch, allowing us to measure what the actual value of Neff was. The process is exquisitely sensitive. The presence of additional relativistic particles would have affected the expansion history of the universe in the few 100,000 years before the CMB was released. More relativistic energy means a stronger gravitational pull, causing the universe to expand faster. A faster expansion rate would have left its mark on the CMB in several ways. It would have altered the relative sizes of the acoustic peaks. More significantly, it would have changed the precise balance of time between the moment of recombination, when atoms formed and the CMB photons were set free, and the moment when the universe transitioned from being dominated by radiation to being dominated by matter. This transition leaves a specific signature on the largest angular scales of the CMB. By analyzing these subtle details, satellites like Planck can measure Neff. The results from Planck are fascinating because they sit in a tantalizing gray area. The measured value is around 3.24, give or take a few tenths. This is slightly higher than the standard model prediction of 3.044. The discrepancy is not yet statistically significant enough to claim a definitive discovery of new physics. It's currently at the level of about 1.5 sigma, meaning there's still a reasonable chance it's a statistical fluctuation. But it's a persistent hint, a suggestion that the early universe's pantry of light particles might have contained something extra, an ingredient not included in our current particle physics cookbook. This potential extra ingredient is what cosmologists call dark radiation. It's a catch-all term for any form of relativistic energy that isn't photons or the three known neutrinos. The most compelling candidate is a hypothetical particle known as a sterile neutrino. Unlike the three active neutrinos we know, which interact via the weak nuclear force, a sterile neutrino would interact only through gravity, making it even more elusive. If sterile neutrinos exist, they would have been produced in the hot Big Bang and would contribute to the relativistic energy density, nudging the measured value of Neff upward. Other possibilities include entirely new light particles predicted by theories that seek to go beyond the standard model, or even more exotic concepts like light particles resulting from the decay of other primordial relics. The implications of a confirmed discrepancy in Neff would be monumental. It would provide the first direct cosmological evidence for physics beyond the standard model of particle physics. While particle colliders like the Large Hadron Collider smash protons together at incredible energies to search for new particles, they are blind to extremely light, weakly interacting particles like sterile neutrinos. The early universe, however, was the ultimate high-energy laboratory. A measurement of Neff from the CMB is effectively a measurement made at energies trillions of times higher than what we can achieve on Earth. It probes a frontier of physics that is otherwise completely inaccessible. A higher Neff would be a direct message from the first second of the universe, telling us that the family of fundamental particles is larger than we thought, and that the cosmos was once host to ghosts even more phantom-like than the ones we already know. After the primordial fireball cooled and the cosmic microwave background was set free, the universe entered a period known as the Cosmic Dark Ages. For millions of years, it was a vast, featureless expanse filled with a fog of neutral hydrogen gas, utterly dark and silent, with no stars or galaxies to break the monotony. But this darkness was not permanent. An epic transformation was brewing, a revolution that would flood the cosmos with light for the very first time. This is the story of the epoch of reionization, and the cosmic microwave background holds a crucial yet puzzling clue about when and how this cosmic dawn unfolded. The mystery we encounter today is not about the CMB's temperature, but about a subtle shadow it casts, a measurement called the optical depth to reionization. To understand optical depth, imagine you're trying to see a distant lighthouse on a very foggy night. The thicker the fog, the dimmer and more reddened the light appears by the time it reaches your eyes. The fog absorbs and scatters some of the light along the way. In cosmology, the neutral hydrogen gas that filled the universe after the CMB was released acted like that cosmic fog. It was transparent to the CMB light itself, but it was completely opaque to the higher energy, ultraviolet light that the first stars and galaxies would eventually produce. As these first luminous objects ignited, their intense UV radiation began to burn away the fog, ripping electrons away from the hydrogen atoms in a process called ionization. This created growing, transparent bubbles in the neutral hydrogen, allowing light to travel freely. The entire universe was gradually reionized. The key question is, when did this happen? The CMB provides a way to measure this by looking at a secondary effect. When the CMB photons, on their 13.8 billion-year journey to our telescopes, encountered this late-forming fog of free electrons in the reionized bubbles, a small fraction of them were scattered one last time. This secondary scattering left a specific, large-scale signature in the polarization of the CMB. The strength of this polarization signal is directly related to the total number of electrons the photons encountered along the way, in other words, the total optical depth to reionization. It's a measure of how much fog the light had to travel through after the initial CMB release. A higher optical depth means reionization happened earlier and was more drawn out. A lower value suggests it occurred later and was more rapid. The latest data from the Planck satellite gives us a precise value for this optical depth. The measurement points to a universe that was half reionized by the time it was about 500 to 700 million years old. This might seem early, but here's where the mystery emerges. When astrophysicists run sophisticated computer simulations of the formation of the very first stars and galaxies, based on our best understanding of gravity and gas physics, many of these models suggest that reionization should have started even earlier. The simulations often produce enough ultraviolet radiation from early, massive stars to begin clearing the hydrogen fog closer to the 200 to 400 million year mark. The observed optical depth is lower than what these simulations predict, indicating that the actual process of reionization may have kicked off later than our theoretical models suggest. This discrepancy forces us to reconsider the nature of the universe's first light sources. Perhaps the earliest stars and galaxies were less efficient at producing ionizing radiation than we think. The first stars, known as population 3 stars, are theorized to have been behemoths, hundreds of times more massive than our Sun and incredibly hot and bright. But if they formed surrounded by thick cocoons of gas that absorbed much of their UV light before it could escape into intergalactic space, their impact on reionization would have been delayed. Alternatively, maybe the very first galaxies were simply rarer than our simulations predict. If structure formation in the early universe was slightly slower, it would have taken longer to build up a critical mass of galaxies capable of flooding the cosmos with enough UV radiation to do the job. But there's another, more exciting possibility, that we are missing a key contributor to reionization altogether. What if the first stars and galaxies weren't the only players? A growing body of research suggests that supermassive black holes in the cores of these early galaxies' active galactic nuclei could have played a vital role. These monstrous engines, accreting vast amounts of matter, would have produced unbelievable amounts of high-energy X-ray radiation, which is far more efficient at penetrating dense gas and ionizing hydrogen than UV light from stars. If a significant fraction of the early galaxies housed these bright quasars, reionization could have been a more rapid and later process, potentially aligning with the CMB's optical depth measurement. The challenge is that we have yet to observe a large population of these early quasars, making this an active and thrilling area of research with the James Webb Space Telescope. The optical depth to reionization is therefore more than just a number. It's a bridge connecting the smooth, dark universe revealed by the CMB to the vibrant cosmos of galaxies we see today. The tension between the observed value and theoretical predictions is a clear signal that our understanding of the universe's first chapters of structure formation is still incomplete. It pushes our observational frontiers to their limits, challenging us to find and study the faintest, most distant galaxies ever seen. By pinpointing the exact timing and sources of reionization, we will not only solve this mystery, but also complete our story of cosmic evolution, from the simplicity of the Big Bang's afterglow to the dazzling complexity of the galactic tapestry we call home. As we've journeyed through these 20 mysteries, a subtle but profound question begins to surface, one that goes beyond any single anomaly to challenge the very process of cosmology itself. Why is it that as our technology grows more advanced and our maps of the cosmic microwave background become exquisitely detailed, these strange features, the cold spot, the hemispherical asymmetry, the axis of evil, do not simply vanish? If they were mere statistical noise, we would expect them to be washed away by the tide of better data. Yet they persist, lingering at the edge of statistical significance like a whisper we can't quite ignore. This resilience forces us to confront a critical meta-mystery. Are we witnessing the slow erosion of minor data quirks, or are we seeing the first cracks in a foundational scientific paradigm? The official stance of many within the scientific community, including the teams behind the Planck satellite, is one of cautious skepticism. They argue that we must always default to the simplest explanation first. In a dataset as vast and complex as the CMB, containing billions of independent pixels, it is almost a statistical certainty that some patterns will appear strangely ordered purely by chance. This is known as look elsewhere effect. Imagine you have a carpet with a completely random pattern. If you stare at it long enough, you will inevitably start to see faces, animals, or shapes that seem intentionally designed. Our brains are pattern recognition engines hardwired to find significance even in randomness. When we analyze the CMB, we are effectively staring at the ultimate cosmic carpet, and the fact that we see a few peculiar alignments might just be a cosmic Rorschach test reflecting our own cognitive biases rather than a true feature of the universe. This perspective is strengthened by the fact that we have only one universe to observe. We cannot rerun the Big Bang 1,000 times to see if a giant cold spot appears in 999 out of 1,000 trials. Cosmology is, in this sense, a historical science with a sample size of 1. Any anomaly we detect could be a rare, one-off fluctuation. The universe might simply be a bit lumpier on one side, or have a curiously quiet base note for no deeper reason than that's how the quantum dice happened to land this time. From this viewpoint, the persistence of the anomalies is not evidence of new physics, but a testament to the immense challenge of interpreting a unique, non-repeatable experiment. However, an equally compelling argument suggests that their stubborn refusal to disappear is itself a significant clue. In science, when an unexpected signal persists despite increasingly sensitive attempts to explain it away, our attention should intensify. Consider the history of the cosmic microwave background itself. Its discovery in 1965 was initially considered a possible nuisance, a mysterious background noise that radio astronomers had to subtract from their data. It was only through its persistence and its match to theoretical predictions that it was recognized as the echo of the Big Bang. Today's anomalies might be playing a similar role. Their persistence, especially when multiple independent anomalies like the power asymmetry and the alignment seem to point in similar directions on the sky, raises the tantalizing possibility that they are interconnected symptoms of a single, deeper cause. This leads us to the thrilling and somewhat daunting prospect that we may be on the cusp of a major paradigm shift. The standard model of cosmology, lambda CDM, has been spectacularly successful, passing every major test for decades. But the history of science shows us that even the most successful models are eventually superseded. The persistent anomalies in the CMB could be the equivalent of the slight misfit in Mercury's orbit that hinted at the need for Einstein's general relativity, or the ultraviolet catastrophe that signaled the end of classical physics and the dawn of quantum mechanics. They may be pointing toward a cosmology that is far richer and more complex, one that incorporates features like a non-trivial cosmic topology, a multiverse, or a dynamical dark energy that leaves an imprint on the very largest scales. Navigating between these two possibilities, statistical fluke versus revolutionary clue, requires immense scientific discipline. Researchers must constantly guard against confirmation bias, the natural human tendency to favor evidence that supports their preferred theory. The very act of looking for anomalies once they have been proposed can unconsciously influence the way data is processed and analyzed. The scientific method, with its emphasis on independent verification, peer review, and predictive power, is our best defense against these biases. The path forward is clear. We need new, decisive data. The next generation of CMB experiments, which will map the polarization of the sky with unprecedented fidelity, will serve as the ultimate arbiter. They will either finally smooth away these wrinkles in our cosmic map, or reveal them in such stark relief that a new chapter in our understanding of the universe will be forced to begin. The persistence of the anomalies is not a failure of our current model, but a beacon guiding the next great exploration into the unknown. Now, after exploring over 20 distinct puzzles, from missing monopoles to a lopsided cosmos, we must face a question that synthesizes them all. What if these are not isolated quirks, but interconnected symptoms of a single, deeper issue? This brings us to a mystery that strikes at the very heart of modern cosmology. Do the accumulated anomalies in the cosmic microwave background pose a fundamental challenge to the theory of inflation itself? Inflation has been the reigning paradigm for decades, celebrated for its elegant solutions to the horizon, flatness, and monopole problems. It paints a picture of the universe's birth as a sudden, exponential stretching of space from a microscopic seed, a process that naturally produces a cosmos that is large, flat, uniform, and seeded with nearly scale-invariant Gaussian fluctuations, the gentle, random quantum jitters stretched to cosmic proportions. For a long time, the remarkable agreement between this simple picture and the overall CMB data seemed like an unassailable triumph. Yet, the very success of this simple model makes the persistent anomalies so deeply troubling. Inflation, in its most minimal and aesthetically pleasing form, predicts a universe that is statistically isotropic, looking the same in every direction, and Gaussian, meaning its fluctuations are perfectly random with no hidden correlations. But the data tells a more complicated story. We see hints of a preferred axis, a hemispherical power imbalance, and curious alignments between the largest features in the sky. While each of these signals individually sits at the edge of statistical significance, their collective persistence is what gives scientists pause. It's like a masterfully crafted symphony where most of the notes are perfectly in tune, but a few crucial instruments are consistently playing slightly off-key. One out-of-tune note might be a fluke, but several hint at a problem with the composition itself. In response to these challenges, theorists have not stood idle. The scientific process demands that when data conflicts with a theory, we first try to extend the theory rather than discard it outright. This has led to the development of more complex, nuanced models of inflation. Imagine inflation not as a single, smooth event, but as a more textured process. Perhaps the inflattened field, the engine of expansion, was not perfectly uniform. What if it had a gradient, a slight variation in energy across the primordial patch? This could lead to an anisotropic inflation, where the universe expands at slightly different rates in different directions. Such a model could potentially generate a hemispherical asymmetry or a preferred axis, imprinting a fundamental lopsidedness onto the cosmos from its very first moment. Other proposals involve multiple fields interacting during inflation, creating more complicated dynamics that could produce non-Gaussian signatures or unusual large-scale patterns. The critical question is whether we are witnessing the graceful evolution of a powerful theory, adapting to new data, or the beginning of its eventual demise. Are these more complex inflationary models legitimate refinements, or are they becoming what philosophers of science call degenerate research programs, theories that are constantly being patched up with new parameters to fit inconvenient data, losing their original simplicity and predictive power without offering truly new, testable insights? This is a delicate and essential tension in cosmology. Every time we add a new feature to inflation to explain an anomaly, we risk making the theory so flexible that it can explain anything, and a theory that can explain everything ultimately explains nothing. This debate forces us to consider alternatives to inflation entirely. While inflation is the dominant framework, it is not the only game in town. Competing theories, such as bouncing universe models where the Big Bang was preceded by a contraction from a previous cosmic cycle, or scenarios involving a slow, non-inflationary onset, offer different pathways to a large, flat universe. These alternatives often predict very different signatures in the CMB, particularly on the largest scales where the anomalies reside. For instance, a cyclic universe might naturally leave the largest scales untouched by pre-Big Bang physics, potentially explaining the lack of large-angle correlations. The challenge for these alternatives has always been matching the stunning success of inflation on small and medium scales, particularly the precise pattern of the acoustic peaks. But the persistent anomalies offer them a potential foothold, a set of observations that inflation struggles with naturally. Ultimately, the CMB anomalies serve as a powerful reminder that science progresses not by confirming our expectations, but by confronting our models with stubborn, unexplained data. They are the unresolved threads in the cosmic tapestry, pulling at the seams of our most cherished theories. Whether they lead to a refined inflation, a completely new paradigm, or simply fade away as measurement artifacts, their investigation is driving the field forward. The next generation of observatories, with their unparalleled sensitivity to the polarization of the CMB, will be the ultimate arbiter. They will either finally smooth out these wrinkles in our cosmic map, confirming inflation's simple beauty, or reveal them in such stark relief that a new, more complex, and perhaps more wondrous chapter in our understanding of the universe's birth will be forced to begin. The challenge to inflation is not a sign of failure, but a testament to the vibrant, self-correcting, and endlessly fascinating process of scientific discovery. Yet as we push our standard model of inflation to its limits to explain these curious features, we are inevitably led to a possibility so vast it challenges the very definition of reality. If the anomalies in the cosmic microwave background are not mere statistical flukes, could they be evidence of events that occurred outside our universe altogether? This brings us to the breathtaking frontier of cosmology, the potential multiverse connection. The idea of a multiverse is not a single theory but a consequence that emerges naturally from our most promising models of eternal inflation. In this scenario, the inflationary period that gave birth to our cosmos was not a one-time event. Instead, it is an endless, ongoing process, a foaming sea of spacetime where countless bubble universes are continuously budding off, each with its own unique set of physical laws and constants. Our entire observable universe in this picture is just one bubble in an infinite cosmic froth. Within this framework, a fascinating explanation for certain CMB anomalies, particularly the enigmatic cold spot, emerges. If our universe is one bubble in a multiverse, it's not unreasonable to think that during its infancy, it might have brushed up against a neighboring bubble. The collision between two such cosmic domains would be a cataclysmic event, releasing an immense amount of energy at the boundary. As the collision interface propagated through our young universe, it would have created a disturbance in the primordial plasma, a vast circular ripple. When the plasma finally cleared and the CMB was released, this ripple would have been frozen into the sky as a distinct large-scale feature, a region with a noticeably different temperature than its surroundings. The cold spot, with its unusual size and temperature profile, becomes a prime candidate for such a cosmic scar, a bruise left by a collision with another reality. It is crucial to recognize just how speculative this idea remains. A multiverse collision imprint is a hypothesis of last resort, one that physicists turn to only when more conventional explanations, like the supervoid hypothesis, fall short. The challenge is extraordinary. We are attempting to use observations from within our single universe to infer the existence of, and an interaction with, a completely separate universe with potentially different fundamental physics. Proving such a concept with any degree of certainty seems almost insurmountable. However, this is where the cosmic microwave background earns its status as our most profound cosmological tool. It is quite literally the furthest back we can see in time, the final screen upon which any pre-existing or external events would have been projected. If there is any observable window into the multiverse, however foggy, it is the CMB. The search for such imprints is therefore not pure philosophical speculation. It is a data-driven, if highly ambitious, scientific pursuit. Researchers have developed specific mathematical templates for what the signature of a bubble collision would look like in the CMB data. They search for particular patterns, not just circular cold spots, but also specific distortions in the polarization patterns surrounding them. These templates are then compared against the Planck data in a meticulous hunt for a match. So far, no definitive evidence has been found. The cold spot, while intriguing, does not perfectly match the most detailed predictions for a collision signature, and comprehensive scans of the entire CMB sky have not revealed other, clearer candidates. Yet the very act of looking is transformative. It forces us to ask deeper questions about the nature of our universe's origins. If the cosmos began with a period of inflation, then the multiverse may be an inescapable consequence. The search for its fingerprints in the CMB, even if it ultimately returns a null result, provides a crucial way to test and constrain the wilder extensions of inflationary theory. By failing to find evidence for bubble collisions, we can rule out certain versions of the multiverse hypothesis, refining our understanding of how inflation might have worked. In this way, the CMB acts as a bridge between the solid ground of empirical observation and the ethereal realm of theoretical possibility, a reminder that even the most elusive ideas must eventually face the cold, hard light of data. But if the anomalies we've explored are the tantalizing clues, then the next generation of cosmic microwave background observatories are the powerful microscopes we'll use to finally solve the case. This brings us to our 24th mystery, one that is uniquely about our own future. What will we learn when we look at the oldest light with unprecedented clarity? The journey doesn't end with the Planck satellite. In many ways, it's just beginning. A new wave of incredibly ambitious projects is already underway, designed with the explicit goal of probing the CMB with a sensitivity that was once the stuff of science fiction. These aren't just incremental upgrades, they represent a quantum leap in our ability to listen to the whisper of creation. Leading this charge are projects like the Simons Observatory and its even more powerful successor, CMB Stage 4 or CMBS4. The Simons Observatory, currently under construction in the high, dry air of the Chilean Andes, is a suite of telescopes that will map the CMB with a resolution and sensitivity several times greater than Planck. But CMBS4 is the true behemoth. Envisioned as a network of telescopes at the South Pole and in Chile, it will deploy hundreds of thousands of ultra-sensitive detectors, creating a virtual super telescope with a collecting area far larger than anything that has come before. The goal is to measure the temperature and polarization of the CMB with an accuracy that is orders of magnitude better than our current capabilities. To put it in perspective, if Planck could detect temperature variations of a few millionths of a degree, these new observatories will be able to see fluctuations that are a fraction of that, down to the level of a few tens of nanokelvins. This massive increase in sensitivity is not just for bragging rights, it's the key to breaking the deadlock on the anomalies. For features like the cold spot or the hemispherical asymmetry, the new data will be transformative. With such a sharp and detailed view, scientists will be able to perform forensic-level analyses. Is the cold spot truly a single, coherent structure, or is it a chance alignment of several smaller, colder regions that only appears as one from our vantage point? The enhanced resolution will allow us to see its internal texture, to determine if its statistical properties match those of a rare but natural fluctuation, or if they bear the hallmark of something more exotic like a bubble collision. Similarly, for the large-scale power asymmetry, the new observatories will map the polarization across the entire sky with incredible precision. If the asymmetry is a real cosmological feature and not a foreground contaminant, it should leave a distinct and matching imprint in the polarization data. A confirmation here would be a monumental discovery, forcing a radical rethink of the cosmological principle. Perhaps the most critical target for these next-generation machines is the hunt for primordial B-mode polarization, the swirling pattern that is the signature of gravitational waves from inflation. The lesson learned from the PIXIE-2 experience has been thoroughly integrated into the design of these new projects. They will observe the sky at multiple frequencies simultaneously, from the microwave range deep into the radio. This multi-frequency approach is like having a set of specialized filters. Galactic dust glows brightly at certain wavelengths, while the pristine CMB has a very different blackbody signature. By comparing the signals across all these frequencies, researchers can meticulously separate the faint cosmological signal from the bright foreground interference with a confidence that was previously impossible. This is the only way to be sure that a detected swirl is truly from the dawn of time and not from our own galactic backyard. The potential outcomes are stark and world-changing. One possibility is that these powerful new eyes on the cosmos will finally smooth out the wrinkles. They might reveal that the cold spot is indeed a statistical fluke in a vast dataset, that the hemispherical asymmetry was a subtle artifact of imperfect foreground subtraction, and that the large-scale alignments were simply a cosmic coincidence. In this scenario, the anomalies would fade into obscurity, and our standard lambda CDM model with simple inflation would be solidified as a remarkably complete description of the universe. It would be a triumph of the simple and the elegant, confirming that the cosmos, for all its immensity, operates on fundamental principles we have largely already uncovered. The other possibility is the one that truly excites cosmologists, that the anomalies will not only persist but will be revealed in stunning, unambiguous detail. A confirmed detection of primordial B-modes would instantly open a new chapter in physics, giving us a direct measure of the energy scale of inflation and pointing the way toward a theory of quantum gravity. If the hemispherical asymmetry is proven real, it would force us to develop models of anisotropic inflation or consider a pre-inflationary structure to reality. Either outcome is a win for science, but the latter would be a revolution. These future observatories are therefore not just tools for measurement, they are engines of discovery, built to answer the most profound questions we can ask about our origins. They stand ready to either close the book on 2 decades of cosmic mystery or to tear out the current pages and hand us a completely new story to write. All of these mysteries, from the faint whisper of a hemispherical asymmetry to the profound silence on the largest scales, ultimately converge on a single, humbling point. We have built our entire understanding of the cosmos on a foundation of simplicity and symmetry, on the steadfast belief that the universe is fundamentally homogeneous and isotropic, that it looks the same in every direction and from every location. This cosmological principle is more than just a convenient assumption. It is the philosophical bedrock of modern science, a direct extension of the Copernican principle that we do not occupy a special or privileged place in the cosmos. It is the reason we can look at a distant galaxy and assume that the same physical laws govern it as govern our own solar system. It is what allows us to believe that our view from this tiny rock orbiting an average star is a fair and representative sample of the whole. But what if the bedrock is cracked? The persistent anomalies in the cosmic microwave background present us with a deeply unsettling possibility. If the universe truly has a preferred axis, an axis of evil around which its largest structures seem to align, then the cosmological principle is not an absolute truth. It would mean that on the grandest of scales, the cosmos has a direction, a fundamental handedness that makes one direction different from all others. And the most disturbing part of this revelation, if true, is the curious alignment of this axis with our own local environment, the plane of our solar system. This coincidence is a Copernican nightmare. For centuries, we have been systematically dethroning ourselves from the center of creation, only to be confronted with data that suggests, against all odds, that we might be looking down the universe's central corridor. It forces us to ask, is this a genuine feature of the cosmos, or is it the ultimate cosmic practical joke, a trick of perspective that has fooled us into seeing significance where there is none? The implications ripple out far beyond astronomy. If the universe is not isotropic, it challenges the very notion that the laws of physics are the same everywhere. Perhaps the constants we hold so dear, the strength of gravity, the mass of an electron very subtly across the vastness of space. Our entire scientific enterprise is predicated on the idea that experiments are repeatable and that local measurements have universal validity. A lopsided cosmos would force a radical re-evaluation of this premise, suggesting that our laboratory on Earth might only be giving us a local bylaw, not the universal constitution of physics. This brings us to the most profound role of the cosmic microwave background. It is far more than a fossilized relic of a fiery past. It is the ultimate mirror. When we point our telescopes at this ancient light, we are not just looking back in time. We are holding up a reflection of our own understanding. The anomalies we see are not merely features of the universe. They are the places where our current theories strain and buckle. They are the points where the reflection becomes distorted, showing us the limits of our knowledge. The CMB is a canvas upon which we project our best models of reality, and the places where the paint doesn't quite match the underlying texture are the very places where breakthrough discoveries await. In this light, the pursuit of these mysteries is one of the most noble and fundamentally human endeavors we can undertake. It is a testament to our relentless curiosity, our refusal to be satisfied with a comfortable, incomplete picture of reality. Whether these anomalies are ultimately confirmed as doorways to new physics or explained away as complex illusions, the process of investigating them pushes the boundaries of science, technology, and philosophy. It forces us to build better telescopes, to devise more sophisticated statistical techniques, and to question our most basic assumptions about the nature of existence. The cosmic microwave background, this faint afterglow that has traveled for nearly 14 billion years, continues to be our most faithful guide, not because it provides all the answers, but because it asks the most profound questions. It reminds us that the universe is under no obligation to make sense to us, and that the greatest adventure lies in trying to make sense of it anyway. And so, our journey through the cosmic tapestry brings us to a final, humbling vista. We have traveled from the grandest scales, pondering the impossible uniformity of the cosmos and the eerie flatness of its geometry, down to the most subtle whispers, the strange alignments, the perplexing cold spot, the tantalizing tensions in its expansion and clumpiness. We have seen how this ancient light, this afterglow of creation, is not a simple, solved puzzle but a living, breathing field of scientific inquiry, one that challenges our most fundamental assumptions at every turn. The cosmic microwave background is far more than a fossil. It is an active frontier. Each anomaly, each tiny deviation from expectation, is a potential crack in the edifice of our understanding, a crack through which the light of a deeper truth might eventually shine. The story of the CMB is a powerful reminder that science does not progress in a straight line from ignorance to certainty. It advances through a dynamic dance between theory and observation, where the most exciting moments often occur not when our predictions are confirmed, but when they are provocatively challenged. The Hubble tension and the sigma-8 tension are not signs of failure. They are the sound of the scientific process working exactly as it should, identifying inconsistencies that demand a more profound explanation. The search for primordial gravitational waves and the precise count of neutrino species are not esoteric exercises. They are direct probes into physics at energy scales forever beyond the reach of earthly experiments, using the universe itself as our ultimate laboratory. This incredible journey underscores a thrilling possibility. The next great revolution in our understanding of reality may not require a journey to a distant galaxy, but a deeper, more careful look at the light that has been bathing us all along. The answers to questions about the multiverse, the nature of dark matter and dark energy, and the very first moment of time itself could be encoded in the faint patterns of this 2.7-degree radiation, waiting for a sharp mind, a novel algorithm, or a next-generation telescope to finally decipher them. The mysteries of the CMB are an open invitation, a cosmic challenge issued to curious minds everywhere. Which of these 25 mysteries captures your imagination the most? Does the sheer scale of the horizon problem leave you in awe, or does the bizarre coincidence of the axis of evil spark your curiosity about our place in the cosmos? Perhaps the potential for a multiverse collision, or the stubborn silence on the largest scales, makes you wonder what lies beyond our observable horizon. Share your thoughts in the comments below. Let's continue this conversation about the greatest story ever told. If you've enjoyed this deep dive into the secrets of the universe, be sure to subscribe and hit the notification bell, because our exploration of the cosmos is far from over. There are always more mysteries to uncover, and together we can keep looking into the deepest light.